In this video, I just want to remind you of some definitions and where some things are, and then I want to push forward with talking about R squared, what the correlation squared represents, and I also want to talk about how you might calculate some of these things by hand, even though you won't often have to. So first of all, for the data to the right, find the means for both columns. I had already calculated these. I put these into my lists, and I did one variable stats. Remember, that's in the stat menu. You go over to stat calc. So here is the average budget right there. Here's the average box office, and of course we use this for our average and this for our deviation. Okay, so we've done parts A and B. The correlation, well, the correlation, if you'll recall, that is that's in the linear regression, the LSRL menu. So I've done that. Here's my linear regression model. Okay. So I have the correlation. Remember, that's R. We can put this. And my LSRL, of course, in this case, it's 48.89 plus 1.48. Remember to use the hat. You know, we do the budget hat box office hat equals 48.89 plus 1.48 multiplied by budget. Now, the slope. If you remember how we interpret the slope, the kind of key word is predicted, and it's for every one explanatory. So we say for every one additional $1 million of budget, we predict that the box office will increase by $1.48 million. Okay, since all of these were in millions. So again, for every $1 million budget and increase in budget, we predict that the box office will increase $1.48 million. Now, interpreting the y-intercept, the key here is that we talk about the explanatory being 0 and what that predicts. So in this case, explanatory being budget, if the budget were $0, we would predict that the box office would be $48.89 million. Okay, and again, this is if the budget were 0, we predict that the box office would be 48.89 million. Now, R squared, we haven't really talked about yet, and of course it's right here. It's easy to find. It's just the square of the correlation. This is called the coefficient of determination. I'm going to come back to this a little bit later, but of course R squared will take on values between 0 and 1. All right, and of course the nearer to 1, the better. And we'll talk about that more here in a little bit. Making a scatter plot of this. So I've done that. Kind of drag that in here. Here's my scatter plot. So let's describe this with our regular DOFs. Okay, direction. The direction is positive. Okay, I'll come back to outliers. Form, I think it's linear. I don't think another model would fit better. Strength, it doesn't look very strong. That was not a really, it wasn't a great correlation. I guess 0.57, it's fair. It's not great, though, by any means. I did also graph this with the line put into it, so you could see, maybe help you see the outliers a little bit. What I would say is that Titanic up here, this is definitely an influential point. You could also maybe make the case it's an outlier because it really is going to be a large positive or a large residual, positive residual. But it is definitely an influential point too, because without it, I think the line that slope would be much less than it is. Titanic really moves that slope up. Okay, let's move on to talk about these definitions and how we could do some of these things by hand. So these are some of the definitions we'd seen before. Slope, we already talked about, and we talked about again in the opener. For every one additional unit in the explanatory, the response is predicted to do what? The The y-intercept, when the explanatory is 0, the response is predicted to be what? Well, now we have r squared. And as I said, r squared is the coefficient of determination. And it tells us the percent variation in the response variable that can be explained by variation in the explanatory variable. So for our opener, it was our opening problem. It's the percent of variation in the domestic box office that can be explained by variation in the budget. So that's why the closer to 1, the better. This is a percentage. So if you had an r squared of 1, you'd say 100% of the variation in that response variable is explained by variation in the explanatory variable, meaning there's a perfect relationship between them. You can absolutely predict what's going to happen. And of course, the lower that is, the more we really open ourselves up to other variables. For example, in that opening problem, you can probably think of lots of things besides just a budget, which would lead a movie to be successful. Who was in it? Was it a sequel? You know, what other movies were out at the same time? What kind of reviews did it get? So that's why that r squared was so low. It was only 33%. It's because there are lots of variables that we didn't talk about, but they can contribute to a larger box office other than just budget. Okay, so that's why if r squared is 1, we say, well, no, it's completely explained by the explanatory. But when r squared is low, we have to start searching. There must be other confounding or lurking variables that help us explain why the box office is what it is. Standard deviation of residuals. This is not really a formula you need to know right now, but I did want to just bring it up that we always talk about deviation as adding up the difference between the mean and the individual points and dividing by n minus 1. And here it's the sum of those residuals, so still, the sum of the residuals squared. So still that difference between kind of the line, the average, and what did happen. But here we divide by n minus 2, and the reason, of course, is 2 points determine a line. Okay, so it gives us the approximate size of a typical prediction error. Okay, again, that standard deviation of the residuals, we always said the standard deviation is the typical difference between a data point and the mean. Well, this is the typical difference between the line and the actual points. So we call that the prediction error. So if we wanted to go a little bit further and talk about how we could solve these things by hand, it really comes down to the fact that what we want to do is minimize the residuals, right? We want the residuals to be the residuals squared, because positive and negative we don't really care. We want those to be at an absolute minimum. And I've included the proofs down here. They're small and they really aren't overly important to you, but I did want to include them because it is just some multivariable calculus, where you say, well, this is how you calculate a residual. The line is simply a plus bx. So getting rid of the parentheses, you've got this. And you begin by saying, well, what if I did the partial derivative only with respect to the y-intercept? And if you solve that through, you would end up with this formula that we can solve for the y-intercept by using the sample means. Okay, doing, that the y-intercept will be equal to y bar, the response mean, minus b times x bar. And I think the way to just remember this is that we need a point. Every line needs a slope and a point. And the way we could use the easiest point would just be to say, well, what if the average point had to be on there, the average x and average y? And this formula we actually have talked about before, the way we get the slope. And I think it's kind of it's self-explanatory maybe by thinking we use the correlation to make sure we're going in the right direction. And we have a way of measuring change in y and change in x. But if you look down here, and I know it's small, there is a proof with multivariable calculus and partial derivatives you can do. That is doing simply the partial derivative of your thing up here with respect to the slope, and then trying to set that equal to 0 to try and figure out how to minimize it. I want to do one example where we calculate these things by hand. Let me show you. All right, so this is the data that the class collected when they dipped the Dixie cup into the bucket full of white and black beads, and then counted the number of black beads and the number of white beads. And what I've done here is I've set it up that the black beads is the explanatory and the white beads are the response variable. So basically we're setting this up so that if I told you a number of black beads, you could predict the number of white beads that were in that cup. So let's go to our formula. The slope, we said, was equal to correlation, which really good, 0.972, multiplied by the change in y, so 22.46, and change in x, which is 43.99. And if you actually type this in, this comes out to be 0.50, actually where it rounds to. So then remember the way we get our intercept is we do the y bar, which was 33.39, minus the mean multiplied by x bar, which is 66.72. So this is 0.01. So this means the number of white beads hat, remember that hat, is equal to 0.01 plus 0.5 times the number of black beads. Okay? So let me drag in, because I said interpret the slope, interpret the y-intercept. Let me just drag those in here. So the slope, for each additional black beads, the number of white beads is predicted to increase by 0.5. If the cup contains 0 black beads, it would be predicted that there were, well, apparently 0.0 white beads. Now, I would look at that and think, due to round off there, I bet it actually is 0, but yeah. And finally, the percent variation in the number of white beads that can be explained by the variation in black beads is 0.9, excuse me. It's going to be 95%. Okay. Now, one quick thing I just wanted to bring up here is, I guess, 2 things. First of all, I want you to think in the context of this problem, what this number might represent in terms of the ratio of beads in there. If I said, each bag of beads contained 2,000 beads, if I told you how many bags I bought, could you give me the breakdown of how many black bags and white bags there were with this slope, knowing that for each additional black bead, the number of white beads went up by 0.5? So that's the first thing. And the second thing I just want to remind you of is, if I suddenly changed this around and I said, but what if there were 50 white beads? How many black beads are there? That would require not working backwards like in algebra. It would require you to actually come up with a new regression equation that had, of course, your deviation switched, and of course this correlation would stay the same. Because correlation doesn't change with explanatory and response switching, but the least squares regression line does.